Hel- Hello, hello. Okay, there she is. There she is. There they are. There they are. There. Hello, Katie. Hello, Maria. Hello. Thank you for the wait. Hello, Chris and Michelle Q. Hold on. And again, I'm saying, sorry. Okay. And now the chat. Oh, there's okay. Hmm, Sorry. Oh, good afternoon, Mohammed. Afternoon, Maria. Good afternoon, Freddie. Good afternoon, Jada. Um, Acknowledging correspondence from yesterday. Check. Good afternoon, Marilyn. Acknowledging homework submission. Good afternoon, Harrison. Good afternoon, Michelle Q. Good afternoon, Paulina. Good afternoon, Brooke. Excuse me. Okay. Who have I not? All right. So that's it. Oh, it's Stephanie. Hello, Stephanie. All right. Um, I mean, also hello, Yavi and Cheska, but I mean, they didn't say hello to me, so whatever. Just being silly. Okay. Oh, good afternoon, Allison. Did I say that? And Brooke. All right. Anyway, let's just do some physics. So here on the board is summary of where I think we are right now. Now I'm gonna what I wanted to, today. My main thing is to like start actually going through the other homeworks. Like I want to start plowing through homework 2 and 3. 3 came out. I keep mentioning 2 is like a lot. It's long. It's a lot of exercises. They look very abstract and out of nowhere when you first look at it. But hopefully you'll see as we start going over today, or you've already seen, now that we've got the punchline finally from question 9, homework 1B, hopefully you'll start to see the pattern and the practice that constitutes most of homework 2. Like hopefully it's not that bad once you get used to it. And homework 3 is almost easier, more straightforward than homework 2. Like if anybody is behind in homework at this point, uh, you or if you're getting frustrated, some of you, if you're getting frustrated with homework 2, if you even skip ahead to homework 3, for some of you, it might even be more straightforward. Um, I mean, technically it was due 5 minutes ago, as you know, and some of you have already gotten it back and done a very good job on it. But in any case, I want to start plowing through these homeworks like now, today. You won't have any more for a little while. But the summary of where we are right, oh, sorry. Oh, okay. Thank you. Thank you, direct message person, for that interesting information about certain missing people. Okay. Oh, and good afternoon, Michelle F. Okay. 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 So where we are now, what you're seeing on the board right now, hopefully we'll start seeing sort of, you're going to see this a lot. Like, hopefully it's going to start seeming almost repetitive or redundant to you. But each time these equations that I'm writing on the board here, each time I write them, I'm going to write them slightly differently on purpose, because the main thing we're trying to drum in now is that you shouldn't get too bogged. You want to get more and more flexible in your understanding of this mathematics. And by flexible, what I mean is you notice the mathematics is having less and less numbers involved. It's looking more and more like a bunch of letters, right? Which can look very abstract at first. Um, and you want to start getting used to the fact that it's not any that don't get too attached to any particular letter. Like, for example, the equation that's on the board right now, up until recently, we were writing it in terms of x's. Now I'm going to start writing in terms of z's. Um, don't I that's on purpose, but I don't want you to be thrown by it. I don't even remember if I wrote this on the board yesterday, but Okay, what I'm saying now, we did a bunch of things in homework 1 that were all dealing with a particular mass on a particular physical spring moving back and forth along an x-axis of space, right? And we did all this math about x as it varied in time, t. Well, we did math. We established a differential equation and we solved the differential equation in order to analyze the motion of that mass along the x-axis. What I want to say now, if I haven't already explicitly said this, is the math we did is math. It's true in general. Whether you're talking about x or y or something else like lab number 2 theta, or you're talking about something else like later in the course like electric field. What I'm saying is that everything that we have now discovered about the mass on the spring moving back and forth through positions known as x, all that math will from here on in apply to anything that behaves in any way like a mass on a spring. And in fact, from here on in, we're going to say that anything that obeys the math of a mass on a spring obeys all the physics and all of the details of a mass on a spring. From now on, we're going to say that if z, okay, so I'm on purpose, I'm switching to the letter z. If I didn't already, I don't remember. But I'm on purpose using the letter z now to stand, as it says in brown here. Z is going to stand for a general variable from now on. Any measurable quantity, any measurement, which varies in time. So from here on in, Z stands for any dependent variable, assuming that we're still physicists and time is still our independent variable. So if Z is anything you measure in the lab that varies in time, so could be position along an x-axis for some mass on a spring, or could be angular position theta along an arc as in a pendulum on a string, right? Or could be temperature as in homework number 3, or could be electric field as in a couple of weeks from now. If Z is a measurable dependent variable, and if that differential equation could be said of Z, like if we have reason to believe that Z can be described by that differential equation written in black in the middle of this page, in other words, if the second time derivative of Z is directly proportional to the negative of Z, right? Like that's literally what that thing says right there in English. If the second time derivative of some dependent variable returns that very variable, like is equal to that very variable times some positive constant times a negative sign, then we're going to say from here on in, then Z, the variable itself, the value of Z will from now on will oscillate cosinusoidally, like can be described as a cosine function. It'll oscillate cosinusoidally at a rate, omega, at a rate, an angular frequency of omega, for which omega is necessarily the square root of whatever that constant is in the differential equation. I mean, this is a mouthful, right? I mean, and that's why I'm going to keep writing it slightly differently, and I'm going to keep trying to say it slightly differently. So, eventually one way lands or whatever. But we're saying from everything I'm saying right here, what I'm saying on this page is from now on, the definition and mathematical definition of simple harmonic oscillation, the SHO that I just wrote down means simple harmonic oscillation. From here on in, a simple harmonic oscillator is any system which can be described by that differential equation that particular differential equation. And therefore, therefore any system for which, therefore, the system oscillates back and forth cosinusoidally at a rate omega, which is necessarily the square root of the constant, the positive constant given in the differential equation, right? Again, like I can write this different ways. Like for example, with a mass on a spring, which got us to this conclusion in the first place, the constant in the differential equation was K over M, right? The original differential equation that we found for the mass on the spring was d2x dt squared equals negative K over M x, right? And what we found out was that the x position of that mass could be described by a cosine function. We found out that x equals x naught cosine omega t. Omega, right? So x went back and forth according to a cosine and at a rate of omega, at an angular frequency of omega. And what was the rate of omega for the case of a mass on a spring? It was square root of K over M. What was K over M? K over M was the constant in that differential equation. What I'm saying from now on is the constant in the differential equation isn't always going to be K over M. For the case of the pendulum in lab 2, it was G over L. It could be different things, the constant. But whatever that constant is in the differential equation, the square root of it is the angular frequency for oscillation, right? So that's why from now on, we just write that constant as omega squared, because we're anticipating from now on, we know that it is the square of the rate at which the system will oscillate. Okay. And by the way, the other reason we write it as omega squared is to emphasize that it's necessarily a positive number. The constant itself is necessarily positive, but then there's a negative sign that goes before the entire thing that ensures the restoring force of Hooke's law. Like the negative sign is crucial to this entire affair. The negative sign means we've got something that's always being brought back to equilibrium, like as per Hooke's law. So obviously we're going to start practicing this more and more, especially in homework 2. That's what I'm about to get to. But I'm just trying to say that from now on, anything that obeys that math behaves like a mass on a spring. It doesn't matter whether the variable is x or the variable is y or the variable is theta or the variable is z. And then last point, I'm saying this whole thing is what it means to be a harmonic oscillator. Very, very specifically, the true absolute definition of a harmonic oscillator, like anything that just goes back and forth cyclically is some kind of oscillator. Any motion or any variation that is cyclical at all is oscillation. But oscillation is known as harmonic if very specifically, in fact, I'm even going to write this even more clearly. Hold on. Oscillation is harmonic. Let me make this more explicit. Oscillation is harmonic if it oscillates back and forth at an angular frequency, at a rate, at a cycling rate, right? That is, on the one hand, constant. That's why I wrote omega equals omega naught, right? When I say omega equals omega naught, that's a physics way of saying that omega doesn't change. So first of all, for something to be a harmonic oscillator, it's got to be cycling at a rate that doesn't change, omega. But more specifically, that rate that doesn't change is not a function of initial of the initial value of the variable. In other words, the rate, I'll say it in English, the rate at which, I'm worried I'm going to run out of room. What I'm saying is The key point I'm trying to make now in English, and it is a huge point, but then I will move on. The huge point I'm trying to make now is that omega, the rate at which the oscillator goes back and forth, right? Omega is the rate measured in radians per second at which the oscillator goes back and forth. From omega, you can convert to standard frequency, the number of cycles the thing makes per second. From that, you can convert to period, how much time it takes to do a cycle, however you want to think about it. Omega or F or T, they're all interchangeable, we said yesterday or Monday. That omega, that cycling rate, that angular frequency, the rate at which the thing undergoes full trips, that omega is always just the square root of the constant in the differential equation. In the case of a mass on a spring, it's square root of K over M. In the case of a pendulum, it's square root of G over L. What it always is what it says here is it's always fully determined by parameters. A parameter is a constant material property of the system. A parameter is a specific type of constant. It's a specific type of constant. It's a constant value that is a material property of the system, i.e., a parameter is a constant description of one or more of the ingredients of a system, such as spring stiffness, or such as mass, or such as pendulum string length, right? These are all examples of parameters, and omega is always determined by parameters. What omega never has in it is the other type of constant that describes our system. What omega never depends on, it's saying right here, omega never has Z naught in it, or X naught in it, or theta naught in it. What omega does not depend on is how far out you initially hold the system. How far out you initially hold the system, like the initial value of Z, according to energy conservation and everything in homework 1, however, how far out you initially hold the system is how far out the system's always going to get. Right? Like in the case of homework 1, you start the mass at 15 centimeters from equilibrium. That's where you start it. It goes back and forth, always between 15 centimeters on one side and negative 15 on the other side. So that a place that you initially held it, where you initially had no kinetic energy and all this potential energy, that's the farthest it ever gets, that place. And that place is always where it turns around. We ultimately call that place the amplitude. Amplitude is the initial maximum displacement from equilibrium. It's the turning point from equilibrium. That's what amplitude is. What I'm trying to say here at the top of my lungs is that angular frequency never depends on amplitude. It only depends. So in other words, it never depends on the constant way that you set up the system. It only depends on the ingredients of the system. The angular frequency does not depend on constants of configuration. Again, this is one of those things you might want to write down. I'm getting too bogged down, so I'm not going to write any more about this, but you might want to. I'm saying there's two types of constants involved in all these, just like there's two types of variables, dependent and independent. There's two types of constants. There's constants known as parameters, which are constant material properties of the system ingredients. And then there's constants of configuration, meaning the initial conditions, meaning the way you set up the system. Okay, K, in the case of a mass on a spring, K and M are parameters. X naught, or what I'm calling here Z naught, is a condition, a way you set up the system. I'm here to assert that the hallmark property of a harmonic oscillation is that the rate at which a harmonic oscillator goes back and forth does not in any way depend on how you set it up. It doesn't matter how far away you initially held the mass from the equilibrium. All that matters is how big that mass is and how stiff the spring is. I mean, if we're talking about a spring system, it means you could put the spring and the mass on the table before you even set them up, before you even attach them together, before you even hold them in any kind of place. You could know in advance how quickly this thing is going to oscillate back and forth. That's a very big deal. And then if you do set it up and you put the mass at 15 centimeters and let it go, it'll go back and forth, say at some rate, at some angular frequency. Say it takes like 2 seconds to do every full cycle, like tick, tock, between 15 centimeters and negative 15 centimeters. What I'm asserting right now is if this thing is a true harmonic oscillator, according to all the math that we've now established, if you started all over again and held the mass all the way out to 30 centimeters instead of 15, and you let it go back and forth under this huge amount of space, if you let the thing go back and forth 30 to negative 30, negative 30 to 30, instead of 15 to negative 15, what I'm claiming is even if you force the thing to undergo these humongous swings through space, they're still going to take the same amount of time. Whether it's 15 centimeters or 30 centimeters or 45 centimeters, according to this math, the tick-tock rate is the same in time, regardless of how you set this thing up in space. That is the essence of harmonic oscillation. I'm going to say it one last time, then I'm going to move on. I mean, one last time today. I'm saying harmonic oscillation means an angular frequency that is independent of amplitude. An angular frequency, therefore a standard frequency, therefore a period, that is fully determined by parameters, that is independent of configuration. That's what I'm saying. I'll say it one last time. Harmonic oscillation means the frequency is independent of amplitude. Like that's like the most concise. That is literally the essence of harmonic oscillation. I'm actually going to say it 2 more times, and then I'm going to move on. But this is going to come for the rest of the course. This is going to come up. And by the way, you'll know this is one of those things that you're really getting. If you're just accepting, I mean, I am telling you the truth, and I'm telling you something very important, and I'm just saying it over and over again so you write it down. But if you're accepting what I'm saying, that's good. Like you're a good student, but you'll really know that you really are understanding what I'm saying if you think about it hard enough to realize that it's actually a surprise. If you think about what I'm saying hard enough to realize that actually what I'm saying does not sound like it makes sense at first, then you'll really know you're getting it. Because what I'll say it again, harmonic oscillation means a frequency in time that is independent of amplitude in space. That's what I'm saying. So again, what I'm really saying is I don't care whether this thing goes back and forth from 15 to negative 15, or it goes back and forth from 30 to negative 30, or 45 to negative 45. No matter how big the cycles are, they're still always going to take the same amount of time. That's what I'm saying. You may want to think about that, and you might even want to ask me about it again next week. Like, I mean, if you're really following me, you'll realize that what I must be saying, and I am, I'm saying that a harmonic oscillator must automatically adjust and make bigger cycles go faster, right? Bigger cycles must, on average, be the mass. If it's making bigger cycles in space, it must apparently be doing those cycles faster if it's doing them in the same time as it does the smaller cycles. That is what I'm saying. And if you really think about it more, you'll realize that is possible, because for a bigger cycle, we start with more potential energy. Therefore, we get on the whole more kinetic energy. So but what's amazing is that the numbers work out perfectly. So that whether you go from 15 to negative 15, or you go from 30 to negative 30, you'll always do it in the same amount of time. So I'm going to say this one last time. So then I'm saying for harmonic oscillation, frequency in time is independent of amplitude in space. So you'll really get what I'm saying if you realize that what I'm saying in the end is what a harmonic oscillator is. At the end of the day, a harmonic oscillator is a clock, and all clocks must be built from one kind or another of harmonic oscillators. A harmonic oscillator is something that keeps time regardless of what's happening in space. All clocks, whether they are pocket watches made of springs, little springs, or whether they're grandfather clocks made of pendulums, or they're digital electronic clocks made of something called a resistor capacitor inductor circuit, which we'll get to. One way or another, a clock must be built from harmonic oscillators, because harmonic oscillators keep time regardless of what's happening in space. Okay, that now we're going to come back to that again and again, but that's like the point of that. Now I'm going to just start practicing this. Oh, sorry. Oh, and welcome back, people that were having connection problems. No, yeah, and there is one person I do know was having connection problems and wasn't eating. But anyway, I hope the food was good. What? I'm just saying what? Okay, so now I'm just gonna go to, I'm just kidding, sort of, not at all. I'm now gonna go, okay, so now I'm gonna be more cut and dried, and I'm just gonna start banging through homework 2 and then eventually homework 3. Okay, obviously stop me if you have any, in a way, homework 2 is practice. What it really is doing question 9 from homework 1, it's doing it, but like backwards. If you'll see what I mean. Instead of solving differential equations in homework 2, what it's doing is testing possible solutions to differential equations and seeing if they work or not. So it's like going backwards. So here we go. And what I'm going to do, like often, it's 12:45. What I'm going to do is the very first one I go over here, I'm going to try to do it thoroughly, like 5-step problem solving method, show you exactly what I'm looking for. And then I'll, from after the first problem, then I'll shortcut things and just do answers and stuff like that. But so the very first one on homework 2, it's called derivatives, right? Very first section of it. Okay. And it says given. Now, what I've got to do right away, if you haven't done this homework yet, either way, what you need a diagram. Step 1, DFP. I know the homework sheet didn't provide a diagram, but that's all the more reason that we do have to provide a diagram. And then you might say, well, the homework sheet is like very abstract math. Yeah, all the more reason we need a diagram to be able to picture what this math means. It is a physics class. What kind of diagram do I have in mind? Well, for this, I absolutely, a cosine graph is totally more than fine. Remember the purpose of a diagram. The ultimate purpose of a diagram is that you use the labels in the diagram to define all the variables and constants that you're going to be using in the math, right? The diagram is really there to define the terms of the otherwise abstract math you're about to do. So everything, every letter that you're going to use in the math has to appear as a label in the diagram. So step 1 DFP, I'm going to do a cosine graph. Now, what does it mean to do a graph in physics, especially outside of lab? It doesn't mean I have to do a whole detailed scatter plot with 1,000,000 points. It means I have to show the trend, the shape of the graph. It means I have to label my axes so that I know what the shape means. And I have to label at least one representative point to give a representation and to give a sense of scale of the graph. So here's my graph. We have X is on the dependent axis, T is on the independent axis. The kind of graph it is clearly a cosine graph. So here's a cosine graph. And I got to put in some labels here now of everything that's going to be used in the math. So the point A is right here, right? And this is the point negative, right? Or more specifically, you could even say, if you like, you could say 0, comma A, right? And that's 0, comma negative A. And then there's this omega. What does omega mean? How can I read it from the graph? Well, I can do a label like this. I can say, in this graph that I just provided, the interval between 2 peaks on this graph or 2 troughs or whatever, that interval is capital T, the period, right? The amount of time for one cycle, because time is on the independent axis here. So I've just labeled the amount of time for one cycle, and that allows me then to say that what I mean by omega is 2 pi over that T. Okay, so now everything. And that I would want, you don't have to do this on every single question of the homework, but when you start the homework, start with something like this. Now, every single letter that I'm going to use in the math is explicitly defined by this picture. Okay, so that's my step 1 DFP. Then step 2, and obviously stop me. So then step 2 WIQ. Like, what is the question? Well, I think The first question, it just asks you to take the derivative of x with respect to t, right? I'm just looking in the chat. Okay, we're all here. Okay. Right? Now notice here too. So I'm about to go to step 3. But notice, like here, this is like we're this would make no sense if we hadn't done homework 1, question 9. But now that we've done question 9, notice we're going backwards. Like question 9, we arrived from the physics at this differential equation. And then we did all this guessing and thinking to create a possible conjecture for the possible solution to that differential equation. And then we checked it and verified and found that indeed it was a solution. Well, now we're skipping straight to that. We're just saying, we're just starting with something that is possibly, we're just starting with a function, x equals a cosine omega t. Maybe this is a description of our mass going back and forth in the lab or something. We're just starting with this expression, and then we're going to take derivatives and see if actually it is the solution to a differential equation. We're skipping straight to the sort of guess and verify stage for what it's worth. Okay, so anyway, so dx dt, so I have to take the derivative. So I'm going to step 3, GDP. So this is the part where I have to write down things that are in general true, like general definitions or general principles that would allow me to take a derivative. Now, again, some of you can do this derivative in your head. Some of you are still getting accustomed to this. But if you do this derivative, the derivative of x equals omega, the derivative of a cosine omega t, even if you can do it in your head, you're definitely doing at least 2 steps in your head just somewhat quickly. Let's be sure that we know what these steps are. Again, I'm dragging this out now on the very first one to show everybody. And this is what I would expect that you do on your homework. But then after we do this first one, you don't have to keep repeating all, and neither will I keep repeating all the steps that I'm doing here. But if this were an exam, same thing. If there's a lot of repetition in the exam, you don't have to keep repeating all the time. But at least at first, show all the thoughts. So my GDP is, I'm going to get general now, right? So I'm saying, like, in general, as in a math class, first of all, if y equals cosine of x, what I know from math is that dy dx equals negative sine of x, right? Notice, please, I'm changing colors to blue, but also you might notice I just suddenly shifted my attention to y's and x's rather than x and t's. I'm not doing that by mistake. I'm also not doing it in order to confuse you. It might be confusing. I'm on purpose switching to y's and x's, as I would suggest you do in homework or exams. I'm switching to y's and x's because I'm going to step 3. I'm trying to make a general point about something that's true about derivatives in general. So I'm writing it like the way I would in a math class, right? Then in step 4, I'm going to apply it specifically to the x's and t's here. So again, I'm just trying to get us all a little bit more flexible with letters. Everything from here on is very few numbers for the rest of the physics course. Like, it all becomes a whole bunch of letters, and they can become really confusing if you don't keep track that with all letters. First of all, some letters are variables and some are constants, right? They're all letters, but some stand for quantities that are changing all the time. Some stand for quantities that are fixed in our mind. So some of the letters are just standing for numbers, even if we don't know the number offhand. Of the variables, one will be dependent, one will be independent. Of the constants, some will be parameters, some will be conditions. This is what we want to start getting used to. So don't think that X is special or Z is special or Y is special. Think, is the letter a dependent variable, an independent variable, etc. Okay, so, and again, obviously you can stop me at any time, or you can speed me up too if I'm bogging down. But I'm saying now, what I know from math is that if y equals cosine of x, then the derivative of y with respect to x is negative sine of x. Similarly, I also know I might as well use it. I mean, I'm going to use it, so I might as well write it. Similarly, if y equals sine of x, I know that dy dx equals cosine of x. Just note, one of those two things that I just wrote down has a negative sign in it, the other does not. That's sort of important, right? So these are just general mathematical truths that I'm going to use. to solve this, but I'm also going to say this before I go in. That's like trig derivatives, right? Now I'm also going to say chain rule. I'm sure you noticed, I'm going to need the chain rule to solve the derivative. So let me write down, at least in a concise form, what the chain rule is and how I use it. So in effect, 1, 2. A, B, C. If y equals some function of x and z equals some function of y, right? This is where then the derivative of z with respect to x, right? If you've got nested or composite functions, then the derivative of the entire nested function is the derivative of the outer times the derivative of the inner. And you might or might not have ever seen it written this way before, but I think if you write it this way, suddenly, at least to me, the chain rule suddenly seems like it makes a bit of sense, right? It's saying the entire derivative z with respect to x is equal to the outer derivative dz dy times the inner derivative dy dx. And it sort of makes sense if you see how the dy's are canceling like that. Okay, that's not a proof. That's just a statement of the chain rule, but to my mind, it makes it easier to believe and easier to remember if you write it that way. So now I have a trig derivative. So in other words, so this is trig derivatives, and this is the chain rule. So now I've established my general definitions and principles. So now I'm going to go to step 4 and apply it. To this problem. So step 4. A particular application and work, right? Okay, so I say here, well, let's set this up. Like here we have, so now I'm in the specific problem. So I'm dealing with X's and T's. I'm just looking at the chat. Okay, so here we have like X equals A cosine omega T. So the way I'm going to, so like, let's say, let Z, or sorry, let's, yeah. Well, yeah, let Z stand for omega T, right? Like I'm looking at this as nested functions now. This is a function of a function. In other words, I'm writing it like this. I'm saying, right? Like if I just rewrite this as a function of a function, I can, and again, I'm dragging this out. If you already totally understand this and you understand the chain rule, then even though this might be a slight pain for you, I'm asking, at least on the first time, as practice for the exam, where there is a question like this on the exam, on the midterm exam, like I'm saying, if you understand this, then at worst you're annoyed because I'm asking you to give me a couple extra steps of work, but I am. If you understand what I'm doing now, then I'm asking the first time, write it out like this. If you don't fully understand what I'm talking about, then that's partly why I'm doing this, is to guide you through. I'm saying this is how the chain, I'm applying the chain rule here. I'm saying x equals a cosine omega t is really a function of a function. It's like an inner function called omega t, to which I'm applying an outer function, x equals cosine of, or a times cosine of. So I'm saying this, I'm saying, and again, stop me either, thus, dx so I'm saying, oh, here, okay, so I'm saying the outer function is a cosine of z. The inner function is z equals omega t. That means the derivative of the inner function, is simply omega, right? That inner function. the derivative is just the slope is omega. So I'm saying, according to the chain rule, we would do right. We would take the derivative of the whole outer thing, which is negative a sine, right? Because we've already established the derivative of cosine is negative sine. And then we multiply by the derivative of the inner thing. The inner thing is omega. So now if I fill all this, therefore, I'm saying dx dt equals negative a sine of omega t, all of that multiplied by omega. Basically, I'm just saying chain rule. And then I'm going to clean it up a little bit the way physicists would tend to write this. You could leave it like that, but it's a little messy. We would tend to bring all the constants together, gather all the constants together at the beginning of a function and leave the variables at the end of the function. So we would write it like this, and I suggest you do too. Right? I'm saying at the end of the day, this is the first derivative with respect to t of that function, right? So that's just so that's step 5, the answer. Now, again, I made that a little longer than you might have made it. And from here on in, it can be a little shorter. But I do believe that is the first derivative. Now, I'm not doing anything with it. I was just asked, take the first derivative. So there it is. Now, move a little fast. I mean, obviously stop me. I'm just looking at the chat. Okay. So now the next question it asks is, what's the second derivative? Okay, so from here on in, I'm warning you, stop me if you don't, from here on in, I'm not gonna like write out the steps as much. I'm just gonna start motoring through this. So, second derivative, I mean, I'm gonna write out the steps sometimes, but I'm not gonna always label them as steps. So like the second derivative is the derivative of the first derivative, right? Actually, and pause for, well, I can never resist saying this. If you're like me, you know this thing that I just wrote right here. That means second derivative, right? Well, when you first learned that, if you're like me, you might have, when you first learned that, you might have bumped for a second because it's like the 2 is in the middle, up in the numerator of the fraction, and then the 2 is at the end in the denominator, right? They write like d2x dt2, right? And when you first see that, if you're a normal person, well, and if you or if you're anything like me, when you first see that, you might be like, wait, what? Why did they put the 2 in like 2 different places? Like, what? Why are you putting the 2 in 2 different places? And then if you're like me, or you're like many people, you think about it for 1 second, and then your brain just shuts down and goes, oh, well, it's a freaking math class, math teacher, like whatever. It's just another one of those things that math teachers do. It just doesn't make any sense. And I just have to accept it and move on with my life. And then you forget about it and you move on and you just get used to it, right? But I'm here to tell you that's dangerous. Like, yes, we all do that all the time. We just like accept things that like math professors or physics professors say. And we're just like, oh, yeah, that's like that stupid thing. I'll just accept it and memorize it and move on. But what that does is more and more over time make us think that math doesn't make any sense. And it's all just like a bunch of arbitrary crap that's there to confuse us or to give us more to memorize. That's not the case. The fact is, it does make sense that it's written that way. 2 reasons it's written that way. So I'm just pausing for like a little public service announcement here. The reason second derivatives are written in that funny way, there's always a reason in math, and it's always meant to make it more sense, not less. The reason they're written that way is because the second derivative of x with respect to time means exactly what I've written here. The derivative with respect to time of the derivative. Right? If you think about it that way, in other words, it doesn't mean take the derivative and square it, right? It doesn't mean multiply the derivative by the derivative. If it meant that, then you would put the 2 in the same place in the numerator and the denominator. But we're trying very explicitly to say, don't do that. We're not taking a derivative and multiplying it by itself. We're taking a derivative of a derivative. It's an operation that we're performing on a derivative. So, okay, so first of all, that's why the derivative is written that way. If that helps anybody in any way, good. take it as a larger statement that things in math actually are meant to make sense. They're not meant to be arbitrary. But okay, but be that as it may, I'm also writing it down to say to myself, okay, in order to get the second derivative, I'm just going to take the derivative of what I already have, right? And I'm going to do the same process, chain rule and trig derivative. So I'm going to cut to the chase. Like if my first derivative was this, then my second derivative, my derivative of my derivative, is by chain rule and trig derivatives is this, right? Notice because of chain rule, omega comes out again. Like we do the chain rule again. So we multiply by omega again. So we ultimately get an omega squared there. I'm sure many of you realized when you did this homework. But also notice that we don't take out the negative sign again. Like we're not doing a negative times a negative. A negative got introduced once because the derivative of cosine is negative sign, but then the derivative of negative sign is not cosine, it's negative cosine, right? So the negative sign stayed there when we took two derivatives. That's important, just take a note of that. So this is my second derivative, and that's the answer. That's all it was asking, right? So that's the answer, that's the second derivative. But so what? Right now it's just abstract, math for its own sake. But then we get the reason for this is that we get to the next question, B. It says now so it's asking me to like look at my conclusion here. It's saying, is this original function that I was given, is it a solution to the differential equation to this differential equation, the differential equation that we are now trying to get used to in this class, because this differential equation describes something very, very physical. In other words, what we're really asking here is, i.e., does x equal a cosine omega t accurately describe a simple harmonic oscillator? That's really what we're being asked here. We're saying, does this function satisfy or solve the differential equation for harmonic oscillation? That's what we're being asked. So we're asking, could you use x equals a cosine omega t to predict the place at any given time for something that is obeying the differential equation for harmonic oscillation? That's what we're being asked. Now, I mean, if you were paying it based on our prior classes, I think I'm strongly guessing yes, based on our prior classes. But how would I know that here if I'm just doing this freshly? Well, okay, the differential. I'm just rewriting. And this time it happens to be written in terms of x's. It could be written in terms of y's or z's or whatever. But here's the differential equation, right? Sorry. And the solution that we're testing is, so the question is, does one fit the other? Well, how do we know? Well, we just found, and again, you don't have to write all this out every single time, but we just found that if x equals a cosine omega t, then d2x dt squared equals negative a omega squared cosine of t, or cosine of omega t. It's like, so what, right? Well, I'll write it again on the next page. I'm just rewriting it so you can see it on one page. We just found this. But multiplication is commutative. You can switch around the order of multiplication. It doesn't change anything. So it's perfectly fair to write that d2x dt squared equals negative omega squared a cosine omega t, right? Like, in other words, if we take two derivatives of, this is all assuming that we're testing x equals a cosine omega t. Apparently, if x equals a cosine omega t, if you take two derivatives, what you get is negative omega squared a cosine omega t. Like, so what? Like, what does that show? Am I running in circles? What does it mean? Well, the key thing is it means this. This thing right here is x, right? That thing right here is literally what we are testing out as the expression for x. So evidently, right, and that's the key, is to make that substitution or make that recognition. Evidently, if x equals a cosine omega t, then two derivatives of x returns a negative sign times a constant times the original x. That is the differential equation. So the answer is yes. The answer is yes to this one. A cosine omega t does satisfy the original differential equation. It is a harmonic oscillator. And it does almost, until you get used to this, it almost seems like we're running in circles. But part of the reason there's a number of different exercises on this sheet, and part of the reason that some of the times the answer is yes on the sheet, and sometimes the answer is no, is it's trying to show you that this is not actually a circle. We actually did just discover something. Like, the key point, I'll say one last time and I'm going to move on. Like, it doesn't always work. It worked for this function. What I'm saying is the differential equation for harmonic oscillation says we've got some kind of function for x, or we need some kind of function for x, which, when you take two derivatives of it, you get back it times a positive constant times -1. We're looking for a function that when you take two derivatives of it, you get back itself times a positive constant times -1. If the function does that, then it is a harmonic oscillator. If not, then not. One last one. So like this one, like, so one of the reasons cosines are a very good way to describe harmonic oscillators is cosine does just that, right? The cosine of x is negative sine of x. Sorry. The derivative of y equals cosine x is dy dx equals negative sine of x. And then take another derivative of that and you get negative cosine of x. When you take two derivatives of cosine, you get back to cosine times a constant times -1. That's what we want. Again, not all functions do that. The function x equals 1f at squared plus v naught t. If you take one derivative of that, you get at plus v naught. And you take another derivative of that, you just get a. If you take two derivatives of 1f at squared plus v naught t, you don't get 1f at squared plus v naught t times a negative sign or something. You just get a. That's not the original function, right? So we're looking for functions that when you take two derivatives of them, you get back the original. Evidently, this cosine function does do that. Excuse me. So the answer to B is yes. And the reason, the y is this thing right here, because it spat back, the second derivative spat back the original function times a constant times -1. Now, if we go, I know it's 1 of us, we got 20 minutes. Now we're going to keep practicing. Now, if we go to B cuts to the chase. It just asks you, what about, I'm sorry, that was B. I'm sorry, C now. C asks you, what about x equals a cosine of 5t? Is this a solution to d2x dt squared equals -3x? Okay, now this is a slightly more interesting question. Now, like it's cutting to the chase. The only way I'm going to find out excuse me. Um, the only way I'm going to find out if a cosine 5t is a solution to d2x dt squared equals negative 3x is if I do the same thing I did above, take two derivatives and see what happens, right? So it happens that it actually guides me to do that in step D. It's kind of the question, it's kind of out of order. I mean, so I could start doing it right away. And then D is just asking me to sort of demonstrate the procedure that I just did. But I'm going to do it. I'm also just going to warn you, like, this is, I mean, it's practice. These are exercises. But see, as you're getting used to this, you should recognize C is definitely talking about harmonic oscillators. Like, again, it's definitely asking, is this particular function a solution to the harmonic oscillator diffeq, a differential equation? We're definitely still talking about harmonic oscillators throughout this whole thing, because that's the physics we're interested in. But that doesn't mean that the answer is obviously yes all the time. You'll see what I mean. So we're going to take derivatives now. We're going to take derivatives. So the function that I'm looking at, the function that I'm considering, apparently is a cosine of, oops, sorry. Oh, wait, sorry. Oh, sorry. There's something in the chat. I'm sorry. Hold on 1 second. Hey, I'm just writing this before I forget. Okay, no, wait, let me look at the sorry, I missed the chat. Oh, a long time ago. I'm sorry. Wait, when we so we had to see. Oh, thank you, Mohammed. Sorry. So Mohammed totally was like all over this. He should submit for points. My bad that I got all carried away and didn't see that. So thank you, Mohammed. That's awesome and cool. And now wait. Then there's something in the direct chat. Oh, okay. Maybe, well, you can stop me if it's already been cleared up. I'll move on, but just in case, because someone, I did. Oh, okay. Thank you. Oh, total points for so deeply paying attention and helping the class to that direct chat person. Okay, awesome, awesome. All right, so I'm moving on. So I've got this derivative here. I mean, I've got this function here. I'm going to take derivatives of it. And I'm going to take two. I'm always taking two because the differential equation refers to a second derivative. And that's what tends to happen in physics. So I take the first derivative, dx dt. I'm cutting to the chase again because it's the same procedure: chain rule, trig derivatives. So I'm going to say the first derivative is negative a times 5 sine of 5t, like from chain rule. And a cleaner way to write that really is negative 5a sine of 5t. That's just a more customary way to write it. So that's the first derivative. Then the second derivative, which I need, same thing happens again with chain rule, all that. So I get negative 25a cosine of 5t, right? That's the second derivative. Now that definitely is a harmonic oscillator, no question about it. But the question is, does x equals a cosine 5t satisfy, or for this? Well, no, it doesn't. Close, but no cigar. Because here's the substitution this time, like this right here, just like before, that is x, right? But so that means if x is a cosine of 5t, then d2x dt squared equals negative 25 times x. But the question that's being asked is, does d2x dt squared equal negative 3 times x? Right? I mean, that's different. In other words, the answer to this one is no, because 25 does not equal 3. Like literally, like that's the reason. They're similar formats, but they have two different constants. Physically, what just happened was this is a simple harmonic oscillator. It is. But it's a simple harmonic oscillator with omega equals 5 radians per second. It's some mass on a spring going back and forth at 5 radians per second. In other words, at almost 2 pi radians per second, at almost a cycle per second. That's what this is. Or a pendulum going back and forth at almost a cycle per second or whatever. But this thing that we were trying to fit to, this is also a simple harmonic oscillator. No question. These are simple harmonic oscillators. But this one has an angular frequency of not 5, not 25, not 3, but the square root of 3. If you're following what we've been doing, you'll see why I said that, right? This is from the first page of the notes, from the first 5 minutes of class today. Like if the differential equation is second derivative equals negative times a constant times the variable, then you have a harmonic oscillator oscillating at a frequency, an angular frequency, that is the square root of the constant. Like just go back and look at the first page. In other words, these are both simple harmonic oscillators, but with different angular frequencies. If they're both masses on springs, they're two masses on springs that are going at different rates. Why? Because one has a stiffer spring than the other, or one has a heavier mass than the other, or both. Both SHOs with different angular. So they're not the same. So one function does not satisfy the other. Okay, so that's the answer to that one. So we have 11 minutes. Oh, okay. Now, wait. Oh, and there's Muhammad again. That's awesome. Sorry, I missed it again, but only by 4 minutes this time. The double derivative, right, of a cosine 5t equals negative a. Right, perfect. So Muhammad, perfect. And if other people, if you're understanding what Muhammad's saying, then you're perfect too. Like, then you get it. So awesome. And everybody should submit for points, except for everybody who shouldn't. All right, so that's that one. We can make more tracks now. Now it gets a little redundant now for a little while, so I'm going to do this. All right, and D we just did, in effect. We just did C and D, just kind of out of order. Now E is the same thing. I'll do it super fast. E is like a review of the exact. It's just trying to get used to the fact that whether you call it omega squared or K over M or G over L or whatever that, or 5 or 3, whatever that constant is, that's what it is. The constant of the differential equation, it is always the square of the angular frequency, whatever you call it. So very quickly, in fact, I'm not even going to talk about this. I'm just going to write it. So if you go to E, and I don't know why the labeling got messed up here, but if E, sorry, E x equals a cosine. Then oops. And that's the first derivative. And the second derivative, is that, or in other words, that, or in other words, so that definitely is a harmonic oscillator. That's our original harmonic oscillator. That is literally a mass of M on a spring of stiffness K. That's where this all came from in the first place. So it's just practice. I mean, there's not much more to say about that. So that's that one. We have 8 minutes. Okay. Okay, now F, which is where we're going to end. I'm just looking. Okay, there's nothing in the chat. All right. This F is probably the last one we're going to do. F is worth doing because now it advances our knowledge. Like it gets into slightly new territory. F says, so F takes our cosine function and it sticks a 3.5 in there. The 3.5 is an arbitrary number. Like it's a number and it's there to see like what happens with that number, but it doesn't matter what the number is. It could have been any number. So and again, I don't know why this is called 3, not 1, but whatever. It asks for the derivative. So we're going to do the same thing as always, trig derivatives and chain rule. But now let's be careful. Notice if you do the chain rule, well, yeah, I'll just write it like this. Notice the derivative of what's inside here, the derivative is still just omega, right? It's omega plus 0. I mean, it's the derivative of omega t, which is omega, plus the derivative of the number 3.5. But the number 3.5 is a constant, so the derivative of that is 0. So the derivative of the inner function is still omega, just like before. So nothing changes in the chain rule or anything like that. When we do, we get like the 3.5 just gets carried along for the ride. It doesn't affect the derivative. And same thing when we do the second derivative. It gets carried along for the ride again. So then when we get to, so those are the answers to F. So then when it gets to G, so that's an answer and that's an answer. When we get to G now, it says, so is that X a solution to d2x dt squared equals negative omega squared X? Well, well, I'm going to say yes, it is, because we just found out that d2x dt squared equals, we just found out equals negative a omega squared cosine of that original thing. And again, multiplication is commutative. So right. Evidently, what this means, with 4 minutes left, this means like I'm saying, evidently, even if you stick a number like 3.5 into the parentheses of the cosine, apparently, even though it looks like it changes something, it doesn't change the derivatives. So you could stick that into the original x, and you'll still, when you take two derivatives, get back the original x times a constant times -1. So evidently, when we thought x equals a cosine omega t was a solution to harmonic oscillation, what we're now realizing is indeed it was a solution. The original thing, x equals a cosine omega t. We're now realizing that's a solution, but it's not the only solution. Or put another way, it's a particular solution. It's not the most general solution. What we're realizing now is that evidently we can stick any constant we want into, like, there was nothing special about 3.5. It was just that it was a constant. So we could stick any constant we want into that parentheses and still describe a simple harmonic oscillator. And all of this time for the last couple of days, when we haven't been sticking a number there, really what we've been doing without realizing it is sticking the number 0, right? We've been really saying x equals a cosine omega t plus 0. And now we're saying, you know what, even if it's not a 0, it's still okay. So evidently, so I'm getting general again. I'm going to end here. I know we have 2 minutes. Evidently, if d2z dt squared equals negative omega z, then what we can really say in general is z equals z naught cosine omega t plus any positive or negative constant that doesn't have to be 0. Right. And from now on, I'm going to call that constant, that thing is the lowercase Greek letter phi. And from now on, it's going to be called the phase constant. And it must be measured in units of radians. In other words, 3.5, that 3.5 must have actually tacitly meant 3.5 radians, because you can't take the cosine of anything other than radians. And omega t is in radians. You can't add anything other than radians to radians. So phi from now on can be in there. It's a phase constant measured in radians. What does it represent? And this is where we're ending. What does phi physically mean? Phi is a head start or a delay in the cycle. For example, if phi is pi over 2 radians, if you remember always, and I'm looking at the clock, we have 1 minute. If you remember always that 2 pi radians is a full cycle, then pi over 2 radians is a quarter cycle. Then we started our stopwatch t equals 0 a quarter way into the cycle. Like, if this is the last thing I'm saying, I'm putting down the pen. If phi is 0, then that means we started our stopwatch when the oscillator was at amplitude position, the natural thing to do. But if phi is pi over 2 radians, that means it has a quarter of a cycle head start or delay in terms of our timing. It means we didn't start our stopwatch until the thing was at the equilibrium position, a quarter of a cycle in. That's just an example. But that's what phi is a phase delay or a phase shift, if you like. And that becomes useful when we have more than one oscillator, which we do next in this class. So, okay, you've been very patient as always. So I'm done. Okay, so have a very nice, so there's no new homework yet. So just catch up to where you are. I'll hang out for a minute or two if there's any questions, although I do have a meeting right after this, but yes, have a good, right. So have a good, bye. Yes, bye.
Bye, Professor.
Bye, have a great day. Have a good day.